So, yeah, it's about as full as it's been recently. Okay, so last time I started just going through a bunch of the problems that didn't have solutions on D2L as we get ready for the test next week, and I'm just going to keep doing that. So the first one I'm going to do is number 4 from control volumes number 1. So this one is a diffuser. The fluid is refrigerant 134A. We have tables for that. It gives pressures in crazy units. We'll convert those. And speed in crazy units. So it's a diffuser. We know the speed at the beginning. We're assuming 0 speed at the end. We have the pressures. It's steady state, ignoring potential energy, and we want to figure out the exit temperature. Okay, so control volumes, part 1, and this is number 4. So it starts out with a pressure of oh, Marshall, this is one of the ones you sent me an email about.
Oh, okay, yeah.
So this is the one where the tables we have don't go up high enough.
Oh, yep.
Okay, so P1 is, after you convert, 689,476 pascals. And the speed at instant 1 is 366 meters per second. And it goes through a diffuser, which means the pressure is going to be higher and the speed is going to be lower when it comes out. So the pressure P2 is 2.07 megapascals. And we're going to assume that the speed is 0. And this is that refrigerant we have the table for, and we want to figure out the temperature at the end. Okay, well, it's a diffuser. We know we're going to use the control volume first law. So dE dt is equal to Q dot minus W dot plus, it's steady state, so I'm just going to write the M's as the M dots as M dot times the quantity HI plus VI squared over 2 plus GZI, and then minus what's happening at the exit, M dot times the quantity HE plus VE squared over 2 plus GZE. Steady state, so the energy rate of change goes away. There is no heat transfer. And this is a rigid thing, so there's no work done by the control volume. We're ignoring potential energy. And then we're treating the speed at the exit as 0, so that goes away. And so now you can we have zeros equal all this stuff. That means that m dot we can remove from the equation, and we get 0 is equal to hi minus he plus vi squared over 2. For the diffuser, we know that he is going to be higher than hi. So I'm going to write this as he minus hi is equal to vi squared over 2. And now both of these two sides are going to be positive. So now the question is, so far I haven't really thought about this problem at all. I know it was diffuser. So I just went through and I knew it was going to be the control volume first law. So I just figured out what we got from that. And this is what we get. So now let's think about like our strategy. We're trying to come up with a temperature at the second instant. Well, we have a pressure at the second instant, which means if we can come up with one more property that's in a table, we can do sort of a reverse lookup on the temperature. And so one of the properties that's in the table is the enthalpy. So let's calculate the enthalpy at the exit. And then, ideally go to a table where the pressure is our pressure, 2.07 megapascals. And if we had that, then we would just look up the temperature. Okay, so I'm going to rearrange this. He is equal to hi plus vi squared over 2. And now that's all stuff we can calculate. So he, we aren't given hi, but we are given a pressure, and let's see, what else does it say about this?
Yeah, so we get the exiting enthalpy because we already know, so we get hi from the P1, V1 condition.
From the P, let's see.
I think that's what it was. What's that? Oh yeah, that's velocity, you're right.
Yeah. So what do we have here? So so we have the pressure and the speed. Oh, it's saturated vapor. That's okay. So I missed that. So at the start, this yeah, this is great. I love this. So at the inlet, at the input, it's a saturated vapor, which means the pressure is enough for us to look up this enthalpy. So this inlet enthalpy is 261.85 times 10 to the third joules per kilogram. And then that speed is 366, so speed squared over 2. Remember, it's easy to make the mistake of taking the values that they give you in the table for the properties and mixing that up with your kinetic energy. Well, your kinetic energy is probably going to be in SI units. The tables give all the energy related stuff in kilojoules, and so those will be a unit mismatch. So be careful with that. You need to write that enthalpy in joules per kilogram. Okay. And so this enthalpy at the exit is 329 times 10 to the third joules per kilogram. Okay, so now what we know at the exit is we know an enthalpy and we know a pressure. And if we had a complete enough table, we could just look this up. Our tables only go up to 1.6 megapascals. But if you look up a table online, just Google refrigerant 134A table online. One popped up right away that went up to 2 megapascals. And the enthalpies don't change very much with the pressure. So a table of 2 megapascals is going to give you answers that are pretty close to 2.07. So I just used the 2 megapascal. So I used a 134A table at 2 megapascals. And it told me that H1 is equal to 322.3 times 10 to the third joules per kilogram at a temperature of 100 degrees Celsius. And there's an enthalpy of 334.1 times 10 to the third joules per kilogram at a temperature T2 of 110 degrees Celsius. These ones and twos now are new. It's not the ones and twos I was using at the beginning. This is just for an interpolation. And so to find the temperature where, now we want to do an interpolation to find the temperature when the enthalpy is 329 in between these two. So the temperature is equal to 100 plus the quantity 110 minus 100 divided by 334.1. You can leave off the times 10 to the third when you're doing this, but I'm just going to put it in. Minus 322.3 times 10 to the third times our desired enthalpy, 329 times 10 to the third minus 322.3 times 10 to the third. And you get that the temperature is equal to 105.7 degrees Celsius. So the speed goes way down, the pressure goes way up. We didn't look at what the temperature was before, but we are at a pressure of this is vapor. Click, 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 click. Okay, so this is so at the inlet, we had a saturated vapor at a pressure of about 0.7 megapascals. So I'll go down here to, so in between these two, We had a saturated vapor. This is in bar, so we need 7 bar. So the temperature at the start is 27, 27 to 31 degrees Celsius, somewhere around 30 degrees Celsius. And when it comes out the other side of the diffuser, the temperature's gone up to 106 degrees Celsius.
Yeah, which makes sense because as I'm trying to think of it, just so I, can compare when I'm going through the problems, example of like the nozzle versus a diffuser, because compressed air, like in a can, would be a nozzle, which that always gets colder, just everyone knows the law.
That's right, yeah.
So it makes sense that a diffuser should get warmer than at the end.
Yeah, right, right. Okay. Yeah, if you compress a gas and don't do anything else to it and don't let any heat escape, the temperature goes up.
Yeah.
And if you let it expand, the temperature goes down.
Yeah, yeah.
Yeah.
Okay.
Any questions about that one? Okay, so the next one I'm going to do, I'm just sort of going through all the ones that don't have solutions on D2L. So now we're going to control volumes 2. And I'm going to start with number 2. So this one's a turbine, steady state, and 23 megawatts of power is developed. It's steam, so we can use the water tables. And the steam flow rate in mass is 40 kilograms per second, so we're going to know m dot right away. At the inlet, there's a temperature of 360 degrees Celsius and a speed of 35 meters per second. It's steam at the start. And it exits as a saturated vapor at 0.06 bar with a given speed. We're going to throw away potential energy, and we want to figure out the pressure at the pressure at the inlet, sorry. Okay, so this is control volume number 2. And we're starting with problem number 2. We're given the mass flow rate is 40 kilograms per second. At the inlet, we know that the temperature is 360 degrees Celsius. The speed is 35 meters per second. And the pressure is what we're trying to find. It goes through this turbine and develops an amount of power of 23 times 10 to the 6th watts. So putting that in SI units. Does it make sense that this W dot is positive for a turbine? Like, think about what a turbine does.
Yeah, because it generates power?
Yeah, it generates power, right. So this has to be positive. And then when it comes out the exit, it's a saturated vapor. Saturated vapor means that we only need to know one property, pressure or temperature, to look up anything else. And we're given the pressure, so we can look anything up in the table that we want. P2 is 0.06 bar. and the speed is 120 meters per second. So they didn't give us a temperature, but we could look it up. We know we're going to use the control volume first law. So dE dt is equal to Q dot minus W dot plus, it's steady state, so I'll write these as M dots. M dot times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. Steady state means that the rate of change of the energy goes away. There's no heat transfer. We're ignoring potential energy. For turbines, a lot of times we'll ignore the speed too, but in this, the speed is given to us, so we're going to use it. And so you get W dot is equal to M dot times HI minus HE plus VI squared over 2 minus VE squared over 2. So there's our simplified form. And we'll see what of this stuff we're given. We were told what the work developed is. That's 23 times 10 to the 6. And that's equal to, we know the mass flow rate is 40. We don't know either of these yet. We do know the speeds at the inlet, that's 35 meters per second squared over 2. And then at the exit, that's 120 squared over 2. Is there anything we can look up here? We know we can solve for the other one if we can look up one of these. So do we have enough information to look up the inlet enthalpy or the exit enthalpy?
The exit.
Yeah, the exit, it's saturated, so the pressure that we're given is enough to look that up. So HE, this is from the table, is 2567.4 times 10 to the third joules per kilogram. And so you can plug that in. So 23 times 10 to the 6 is equal to 40 times the quantity HI minus 2567.4 times 10 to the third plus 35 squared over 2 minus 120 squared over 2. Solve for HI, and you get 3149 times 10 to the third joules per kilogram. Okay, well, we're given a temperature of 360, so we don't know the pressure, but we know the temperature is 360. We know this is superheated vapor, so we can go to the steam tables and do an interpolation using a temperature of 360. You with me on that? So at 360 degrees Celsius, at a pressure of 2 megapascals, we have an enthalpy in the table of 3159.3 times 10 to the third. I'll call that P1 and H1. And then at a pressure P2 of 3 megapascals, we have an H2 of 3138.7 times 10 to the third joules per kilogram. Okay, so usually the F value that you're trying to interpolate for is not the pressure or temperature, but we're doing sort of like a reverse lookup. So you can think of our F as being the pressure. So the pressure we're looking for is 2. I'm doing this in, well, I guess I'll do it all in SI units. So 2 times 10 to the 6th plus the quantity 3 times 10 to the 6th minus 2 times 10 to the 6th. Divided by 3138.7 times 10 to the third minus 3159.3 times 10 to the third. And then multiplied by the quantity 3149 times 10 to the third minus 3159 times 10 to the third. And it turns out you get a pressure of 2.5 times 10 to the 6th pascals, or 2.5 megapascals. Any questions about that? Remember, one thing to be careful about with the interpolations is remember that so if you're interpolating for like a function f on an independent variable x, make sure that you're doing it with the x's and f's that correspond to each other. Don't just think of it as like the higher value of the function minus the lower and the higher value of the independent variable minus the lower. You know what I'm talking about? This is a case where as the pressure goes up, the enthalpy goes down, you know? And so this fraction has to be negative, okay? So if I had gone 3 times 10 to the 6 minus 2 times 10 to the 6 divided by 3159 minus 3138, I would have made this positive and it would have messed up my answer. Okay. Any questions about that one? Okay, so now let's do number 4. This one is a pump. So a pump in steady state, that's what steadily means, pulls water through a pipe from a reservoir. It gives you the volumetric flow rate in gallons per minute. That's annoying. So like if I ask you a question on a test, like whether units that you're given are annoying or not, like, and it's in gallons and minutes, that's annoying. At the pipe inlet, you're given the pressure and the temperature in Fahrenheit, and you're given the velocity that it's moving. This is a liquid, so you could do this all in, oh, well, that's a speed. I'm sorry, that's not a volumetric flow rate. And then at the exit, it's 40 feet that it rises. It doesn't say anything about the exit velocity. And so we're going to assume that the velocity, if we're trying to figure out the power that it takes to lift it that high, the minimum power it could take is for that velocity to be 0 at the top. So we're going to just assume that that velocity is 0.
Yeah, I kind of question that.
Yeah.
Because wouldn't that violate the conservation of mass?
Conservation of mass.
Or, the
yeah.
water going in and the water going up. Because either the water would actually continually,
yeah.
compress as it goes in, or the amount of liquid coming out has to be the same going in.
That does sound right, yeah.
Yes, the velocity at the exit should be the same as the velocity at the inlet, assuming that.
You're right, yeah. You're right. Yep, you are right about that. Yep.
Because yeah, I saw an example after I did this problem. I was going through the old lectures. And you covered this one last year. And you
okay.
E equal to 0.
Okay.
So.
You're right. And if you did, if you did conservation of mass on it, you would see that assumption that I made when I did that is not valid.
Yeah, exactly. I think on that too.
Yeah, you're totally right. Yes.
The same point, and then I went through and I thought about it. And
yes.
That equation of m dot equal to area
times
volume over, or no, area times velocity over specific.
Right. Right. Well, so okay, so this is number 4. So this is a pump. It's raising water 40 feet. And 40 feet is, I must have that, is 12.2 meters. So at the inlet, we're assuming that it's atmospheric pressure. That's given. So 1.01 times 10 to the 5th pascals. And the temperature at the inlet and at the exit is 17.8 degrees Celsius. That's converted from the Fahrenheit temperature. And the speed, V1, is 12.2 meters per second. And then we're given that thing in gallons per minute, the volumetric flow rate. And so if you convert that to cubic meters per second, that's 1.26 times 10 to the minus 3rd meters cubed per second. And at the end, our change in Z is 12.2 meters. Okay, so do we know the speed at the exit? Well, we definitely know the volumetric. So let's say that we have an input area down here. Of A1, okay. And then here's the pump. and this has an area A2. So do we know the speed at the exit? Steady state conservation of mass says the mass flow rate at the inlet is equal to the mass flow rate at the exit. And this is a liquid. Incompressible. Which means that the volumetric flow rate at the inlet has to be equal to the volumetric flow rate at the exit. And what can we say about the speeds? Well, the volumetric flow rate is equal to, well, actually, instead of using this, let's just go back to the mass. And we know that the area at the inlet times the speed at the inlet divided by the specific volume is equal to the area at the exit times the speed at the exit divided by the specific volume. So those cancel. And what we get is that V2 is equal to the ratio of these areas times the speed at the inlet. Without knowing those areas, we can't know the speed. The assumption I made last year when I was duper, well, I just assumed that the output area was infinite, and then the zero speed.
Yeah.
So, but not really. I didn't think about it, but
I see where your thought process was, just the minimum amount of energy to bring
yeah,
it there.
right. But no, you're totally right. It can't be zero. The speed can't be zero up there, and you can't figure out the speed without knowing that those two are the same. I guess it does say it's a pipe, which maybe you could interpret that, the areas are the same, and so then. So
that's just how I interpret it.
Yeah.
I'm like, well, the only assumption I can make is the areas are.
Yes. So let's assume that A1 is equal to A2, and then so that means that V1 has to be equal to V2. Okay, so let's use that. So this up here, well, yeah. So V2 is the same as what we were given. Well, this is a pump, so we know we're gonna use the first law. So dE dt is equal to Q dot minus W dot plus, we're told it's steady state, so M dot times the quantity HI plus VI squared over 2 plus GZI, and then minus M dot times the quantity HE plus VE squared over 2 plus GZE. This time we're not going to get rid of those. Potential energy terms. Since VI is equal to VE, these two cancel. We're going to assume that there's no heat transfer. It's steady state, so there's no rate of change of energy. We can find that mass flow rate because we know at atmospheric pressure what the density of water is. So when pressure is equal to 1.01 times 10 to the fifth, the density is 1,000 kilograms per cubic meter. If it wasn't at atmospheric pressure, you could look that up in a table as specific volume. And so we know that WCV, W dot, is equal to, so M dot is going to be, where is this? It's going to be this volumetric flow rate, 1.26 times 10 to the minus third, times 1,000. So it's just going to be 1.26 kilograms per second. That's the volumetric flow rate. So 1.26 times the inlet enthalpy. Let me put all this stuff together. So HI minus HE plus, I'll write this as G times the change in the heights. All right, well, can we look up either of these two enthalpies? Well, we don't have to because with the pump, the pressure and the temperature are both the same. So you get the same enthalpy, so there's no change there. So those two cancel. And you get the W dot for the control volume is 1.26 times G is 9.81 in SI units times, you can think of this as 0 minus 12.2 or negative 12.2. And you get an answer of, can someone plug that in for me? 150? Okay, so negative 150.8, and that is in watts. Does it make sense that that's negative? What did we calculate here? Yeah, so we were asked for the amount of electric power that it takes to run this thing, the minimum that it could be, and so that's going to be negative, right? Any questions about that? Okay, let's go back to ideal gases and incompressible materials. Let's start with number 2 on that one. So, okay, we have a known mass of liquid water that starts at 100 degrees Celsius. How does 100 degrees Celsius water, how can that be a liquid? How can that not be a saturated liquid? Because it's a super high pressure, right? So 100 degrees Celsius is the phase change temperature at atmospheric pressure, but this is twice atmospheric pressure, and so it's not at the phase change temperature yet. The pressure is constant, and it sort of walks us through a few things. So what's the specific heat of the liquid water? Then determine the water temperature at saturation. Then C and D are really the questions that it's asking you. So use the assumption of incompressibility of this liquid to calculate the enthalpy change for this process. And then what's the heat added during this process? So what's the amount of energy that you have to add to this water to take it, this 10 kilograms of water, to take it from 100 degrees Celsius to its saturation point? Okay, so this is ideal gases and incompressible materials. Number 2, the starting temperature is 100 degrees Celsius. The starting pressure is 2.1 bar, and that's also the ending pressure. We know at the end it's a saturated liquid. So it's a liquid the whole time, which means we can assume that it's incompressible through this whole process. So the first thing it asks us to look up is the specific heat, it looks like. Is that what I said before?
Yep.
Okay. And so you can find that in like near the front of the table, like if you go to D2L where all the tables are, the one that says complete tables, one of the first few pages there gives specific heats for different materials at different temperatures. And so you can just look this up for water at 100 degrees Celsius. And you get that C is equal to 4.22 times 10 to the third joules per kilogram. Okay, just to refresh your memory, so what's the deal with the specific heat of a liquid? Because remember that the specific heats are these sort of complicated, sort of non-intuitive things. We have that C sub V, that's the partial of U with respect to the temperature, holding volume constant. And we have the C sub P, that's the partial of the enthalpy with respect to temperature, holding pressure constant.
For incompressibles, that would be the same.
But yes, for incompressibles, they're both equal to the total derivative du temperature, and they're equal to each other. So there's just one value you have to look up. For gases, there's different ones. And then for part B, the temperature at saturation for 2.1 bar. Okay, well, that's not in the table, but you do have at P1 of 2 bar, the temperature is 120.21 degrees Celsius. For a pressure of 2.25 bar, you're given that the saturation temperature is 123.97 degrees Celsius. And so you're going to have to do an interpolation. So the temperature is 120.21 plus the quantity 123.97 minus 120.21 divided by, so by the way, you can use any units you want when you're doing this. Like for your independent variable, you can use any units you want when you're doing interpolations because they cancel each other out and you're just left with the units of the thing you're looking for. So I can do this in bar or megapascals or whatever. So I'm just going to write this as 2.25 minus 2. And then we want 2.1 bar, so I'll write that as 2.1 minus 2. And you get a saturation temperature of 121.7 degrees Celsius. Okay, the next thing we want to do is, for part C, is we want to calculate the change in enthalpy. We're going to assume that this is incompressible. We have the specific heat. So C is 4.22 times 10 to the third. And for an incompressible material, that's equal to du, d temperature. And so the change in specific internal energy is 4.22 times 10 to the third times the change in temperature. So what's the change in temperature for this process? Yeah, it started at 100 degrees, it ended at 121.7, so. And so you get that this change in internal energy is 91,574 joules. That's the change in internal energy. The pressure remains constant. So I guess I assumed this was a, oh, well, okay, right, it's a liquid. So since it's a liquid, the volume stays the same. Since it's incompressible, that's the assumption we're making. And so the change in enthalpy, specific enthalpy, is the change in specific internal energy plus the change in PV, pressure times specific volume. Well, this is a constant pressure process, and it's incompressible, so the specific volume doesn't change. So this is 0. And so the change in enthalpy is the same as the change in specific internal energy. 91,574. And then D, it asks how much heat has to be added. Well, are we given, oh yeah, it's 10 kilograms. Okay, so how much heat has to be added? So we know that the change in internal energy is equal to Q minus W. And this is incompressible, so we know that there's no work of expansion. And so to calculate Q, we just have to figure out the change in internal energy. We already figured out the change in specific internal energy. We know we have 10 kilograms of liquid. And so the heat we have to add is just the change in internal energy, which is 10 kilograms times 91,574. And so 915, 740 joules.
I just realized that the specific energy and yeah.
Oh, okay. Yep. So in my answers here, I did units of joules, but those are specific. So that's units of joules per kilogram. So the heat is in joules. Any questions about that one? All right, so now number 6. That's a really quick one. Okay, so show that, I guess, for a monatomic ideal gas, the ratio of Cp to Cv is 5/3. Use the fact that Cp over R is 2.5. So for an ideal gas, one of the things that we're given is that Cp is equal to Cv plus R. Okay, so for an ideal gas, Cv is DUD temperature, and Cp is Cv plus R. That R is not the universal gas constant. That's the one specific to the gas you're talking about. And for a monatomic gas, we're given that Cp is equal to 2.5 R. So subtract R from both sides and you get Cv is equal to 1.5 R. And so Cp over Cv is 2.5 R over 1.5 R. And so that's 5/3.
Yeah, you can prove that same thing just using, isn't it called the kinetic energy theory, or what do we call it?
Yeah, right. I don't remember, but something from physics, physics too. Yeah.
Well, they say NKT, but it would be
Yeah.
1/2 R for each direction, and then you have, X, Y, Z.
Yeah.
Which then ends up making your 3/2 that you needed.
Yeah.
For that 2.5. I should say the 1.5.
Yeah.
Okay.
Yeah, I have a vague memory of that. Yes.
I remember that proof, like, specifically.
Oh, okay, that's interesting.
That one kind of tripped me up when I looked at this, because my mind immediately wanted to just go to the
Right.
kinetic theory.
Okay, the next two are more interesting, I think. So 7 and 8, we're not going to get to both of these today probably, but so 7. So we have nitrogen gas in a rigid tank. So gas in a tank, no matter what happens, as long as it stays gas, the volume doesn't change. Okay, as long as it stays gas, the volume doesn't change. It's at 27 degrees Celsius, gives the pressure 0.1 megapascals. And over, over 10 minutes, energy is transferred to the gas by a resistor, but energy is just put into the gas at 0.12 kilowatts. So that's given as a rate of energy being transferred. And then over this interval, 12.59 kilojoules of heat is transferred. So energy transfer by heat and work are given in two different ways. One's given as a rate and one's given as a total over the interval. So treating the nitrogen as an ideal gas, what's the nitrogen's final temperature and pressure? Okay, so we know the mass, temperature, pressure at the start, and then this energy is taken away, added to it, and we want to come up with the pressure and temperature. Okay, so it's a rigid tank. The amount of gas is 2 kilograms, and it's N2 gas. That's important because it means we can look up the molar mass of it, and also it means maybe we can look up the specific heat of the gas. That we don't have it for every gas, but nitrogen we happen to. We start out with a temperature T1 of 27 degrees Celsius and a pressure P1 of 0.1 megapascals. And over this process of 10 minutes, where we're given that the rate of work is, so it said 0.12 times 10 to the third watts of work is added to the gas. With our sign convention, if work is added to the gas, that's a negative. So So this is 0.12 times 10 to the third watts. And then the heat isn't given as a rate, it's given as a total. And that is, now heat is lost, it says, and so that's negative 12.59 times 10 to the third joules. And we want to find the final temperature and pressure. Okay, so what do we know? We can start out with du dt is equal to q dot minus w dot. This time of 10 minutes is 600 seconds. So let's see, we know we can integrate both of these, and we get that the change in internal energy is equal to the total amount of heat added. So that's negative 12.59 times 10 to the third minus negative, now this would be W dot integrated over the time. So this is 0.12 times 10 to the third times the number of seconds, 600. And this is so that change, did I calculate that? I think, so that change comes out to be, I think, 59,410, is that right? That's in joules.
Yep.
Okay. So we know the change in internal energy. The tables for ideal gases let you look up specific internal energy per mole. And we have a table for nitrogen. So we can look up at the starting temperature and pressure the specific internal energy per mole. And then we have to, if we figure out the number of moles we have of the gas, then we can calculate what the total internal energy is. And that'll let us calculate the final internal energy because we have the change. Okay, so at this starting temperature, at instant 1, the temperature is 300 Kelvin. And the pressure is 0.1 megapascals. And so the table for nitrogen says that CV is 0.743 times 10 to the third joules per kilogram Kelvin. And the molar specific internal energy is 6,229 joules per mole. I wonder if that's kilojoules. Joules per, let's just go with joules per mole. Okay, well, how do we figure out how many moles of gas we have? We know that we have 2 kilograms. So if we look up the molar mass of nitrogen, we can just divide 2 kilograms by the molar mass, and that'll give us the number of moles that we have. The molar mass for nitrogen is 28.02 times 10 to the minus third kilograms per mole. And so the number of moles is 2 kilograms divided by 28.02 times 10 to the minus third kilograms per mole. And that's 71.38 moles. And so with our molar specific internal energy, we can multiply that by the number of moles, and that gives us the total internal energy at that first instant. And that gives 444 times 10 to the third joules. Well, our change in internal energy is the internal energy at the second instant minus this internal energy at the first instant, 444 times 10 to the third. And that's equal to, what we calculated first, 59,410. And so the specific internal energy at the second instant is 503,410. Okay, so at this point, so we have that internal energy. We could figure out what that is per mole and do a reverse lookup. Or we could use the specific heat that we got from the table earlier and say du, the temperature, is equal to where did I put that? 420, 0.743 times 10 to the third. So the change in specific internal energy is equal to 0.743 times 10 to the third times the final temperature minus the starting temperature, We can do it in Kelvin. So this is, what do we have? The change in total internal energy is this. If we divide that by 2, so 59,410 divided by 2, because it's 2 kilograms. And can someone calculate T for me? So this is T2. For which one?
I'm just confused why you divided that 59,410 over 2.
Because this specific heat equation is the specific internal energy, and this that we calculated was the actual internal energy. The 59,410 was in joules. Yeah.
I got 339. Well, I guess 340 after rounding.
Okay, 340 Kelvin. And then we could calculate the pressure using the ideal gas law because it was a rigid tank, wasn't it? Yeah. So we can use the same volume. Okay, so question about using the specific heat to calculate this for a gas, because that can be a little bit dangerous. Is this a reasonable change in temperature to assume a single specific heat like this, you know? We had a change of 40 degrees Celsius. So let's just look up the specific heat in the table at a couple different temperatures and see how much it changes. This is the one you have to go to for the ideal gas stuff. And we're looking for let's see, we're looking for specific heats at different temperatures. We use CV. Okay, so here's nitrogen at a few different temperatures. So at 300 degrees Kelvin, the specific heat for nitrogen, C sub V, is 0.4743. At 350, which is a little higher than we had, it's 0.744. So you get really good results for a change in temperature that small. And you can look at these and see like how big a temperature change you need to get like a considerable change in the specific heat where your stuff would be, where that approximation.
Like we're doing,
yeah,
we don't have to use a relation where we have changing specific heat.
Yeah, or this, I didn't mention this and we're not going to do this, but this is a good thing to be aware of. It's easy to find polynomial like curve fits to specific heats with temperature. So look at, here's a cubic polynomial for now this is molar, so you'd have to do some conversions and stuff. But this you can see is within 1% error over a temperature range of, 1,500 degrees.
Okay, yeah, so to get the exact result, we'd be taking that du dt, setting it
Right, and this is CP, so you'd have to, and our du dt is CV, and this is molar, but with some unit conversions and just, be careful about what specific heat you're talking about. Yes, that's the basic idea. Right. That's right. And so for a change in temperature of 40 degrees Celsius, the way we did it works fine.
Gotcha. Yeah, because I realized I was looking at that, I was like, we never had this one do it.
Oh, yeah, really? Oh, well,
I mean, it's good
there you go.
that one. I remember looking at this question that it didn't come up as that homework, but I think that
Okay.
I got stuck originally was
looking
at that, I'm like, wait a second, there's not a specific heat changing.
Right. And so, and it's nice to know that table sort of shows you where the specific heats are changing if you're thinking of using one,
Yeah.
So.
Our final answer is, only a change of 40, so it doesn't matter that much.
Yeah.
Okay.
Okay. That's it. Thanks.
Thank you.